So in this question, I have the moon of Jupiter going around on this path. I know that the radius here, which is the distance from the center of Jupiter to the moon, is 4.2 times 10 to the 8 meters. What I'm looking for is the mass of the Jupiter, and I also know the period, so the time that it takes for this moon to travel from this point all the way through this dashed circle back to the same point. It's going to take 1.5 times 10 to the 5 seconds. Now, in order to find the mass of the Jupiter, we will probably have to use the gravitational potential equation, which is equal to this, and then we can kind of rearrange and solve for that. But before we get there, we just gonna talk about how we can actually rewrite this equation. So the centripetal force here is equal to the mass times the centripetal acceleration So let's talk about how we can get there. Let's talk about the centripetal force here. Now, the centripetal force is equal to the mass of the moon times acceleration centripetal of the moon. And the only force that is responsible for the centripetal force here is the gravitational force, which is equal to G, small m, which represents the mass of the moon. G is the big constant. Mass of the Jupiter over the distance between the centers to the power of 2. That can be written as equal to m, and which is the mass of the moon, times the centripetal acceleration, which is normally equal to v squared over r. I will write that because we can use the velocity later to get our answer. Now, in order to simplify this relation here, we can cancel out the small moon, mass of the moon. This basically shows that our calculations is irrelevant to the mass of the moon, so it doesn't play any role. Only the mass of the Jupiter is responsible for this and what's happening in this situation. Now, what I'm looking for is the mass of the Jupiter. So if I were to rearrange this for that, I could actually cancel another r here, and I'm left with one r, and m will equal to r times v squared over g. And I'm just going to plug in the numbers, and I will have 4.2 times 10 to the power of 8 meters. And now I don't have the velocity to put in here. So what I'm going to do is that I'm going to use the other page to get that. I'm just going to plug in the number here. And figure out how I can find v. Now, the velocity of the moon is equal to the distance that the moon traveled, which I'm going to call delta x, divided by the time it takes for it to travel that distance, which is the period, and it's given. Now, if I'm solving for the velocity, I need the distance, which is the circumference, and that's equal to 2 pi r over t, which is the period, and it's given. So to plug in these numbers, I will have 2 pi for r. I will have 4.2 times 10 to the power of 5, and the period is equal to 1.5 times 10 to the power of 5 seconds. And if I punch these numbers into the calculator, I should come up with 2 pi times 4.2 times 10 to the power of, sorry, this is 10 to the power of 8, 10 to the power of 8, divided by, open bracket, 1.5 times 10 to the power of 5. So my answer is 17,592.9 meters per second. So that's the velocity of the moon of Jupiter around the Jupiter, of course. So then I can use this in my previous equation, which we did here. So we can plug in 1.17 2.9 to the power of 2. And if I plug everything in, I should get 1.95 times 10 to the power of 27 kilogram for the mass of the Jupiter. That's pretty much it. If you have any questions, please comment them down below, and please make sure to like this video. Thanks.